Smart Cat Door. Authors Irene Lin, Philip Petrakian, Jing Wu, Electrical and Computer Engineering, Carnegie Mellon University, Mellon. Abstract. This system is capable of recognizing cats in a video feed and opening a door automatically. Computer vision detects and tracks movement. Machine learning determines if a cat is present. The goals of the system are to be bidirectional to allow freedom, quiet to not scare the cat, accurate so cats are not locked out and raccoons are not let in, and fast to the cats is not left waiting for the door to opens. A mobile app allows the owner to remote lock and unlock the door. Index terms: cat door, computer vision, machine learning. Introduction. The purpose of this system is to keep unwanted animals out of your home while allowing a pet owner cat to have the freedom of entering and exiting. Current smart cat door use RFID technology and have poor reviews online. Recurring themes in the product reviews were about to desire to keep raccoons out, have consistent and reliable door opening and locking over extended period of time, and to have longer battery life. Others complain in having to retrain the cat to push through a heavier door. In our design, a camera mounted on top of the cat door sends footage to the processor. Computer vision is used to detect and track movement, and a machine learning algorithm is used to decide if the animal is your cat. A panel covering the cat door is lifted by a motor and closes after the cat has passed through. Through a mobile app, the pet owner can remote lock and unlock the door. 2. Design requirements. Assumptions. The pet will walk toward the camera head first. The pet is not covered in anything that significantly changes its appearance. A pet owner's house has Wi-Fi. Requirements. 1. Raccoon gets in 5% of the time. Reasoning. With the current smart and non-smart cat doors, raccoons get in 100% of the time because raccoons are clever enough to lift latches and strong enough to brute force their way in. Any number less than 100% is already an improvement. Facial recognition for humans have around 5% miss rate. So we decided to challenge ourselves to match this. Reasoning. There are times result. 20% of the data set was withheld from testing. Please see the section 5 part B, convolutional neural network for more details on test results. 2. Owner's cat is stuck outside 5% of the time. Reasoning. If a cat enters and exits 4 times a day, then across 5 days the owner gets 1 notification. This is reasonable. Results. 20% of the data set was withheld for testing. Please see the section 5 part B, convolutional neural network for more details on test results. 3. 1.1. For doors open when the cat starts at 1 meter away from the outside. Reasoning. Cats walk 3.3 kilometers an hour, 2 mph on average. When a cat has moved to within 1 meter to the door, we interpret this as the cat having the intention to enter the house. 1.09 seconds. Results. The motor took 1 second to open the door. 4. Detect when the cat is all the way through and close the door after. Reasoning. The door should not close while the cat is still in the middle of the doorway, as to not injure the cat. Results. The door took 6 seconds to close because the PER sensor took a long time to settle. Set curfew, remote locking and unlocking, authorized breeds. Reasoning. There are times when an owner does not let their cat outside. When it's raining outside, the owner needs to be able to set a curfew for when the cat is not allowed to outside. The owner also needs to be able to initialize the system to work with his cat's breed type. Results. Although the mobile app could set locking and unlocking, there was no curfew and authorization for breeds implemented. Consistent lighting for nighttime. Reasoning. Computer vision requires consistent light, and the camera needs to be able to obtain clear footage of the cat even at night. Results. Although the LED was mounted on the door, no testing was done. Seven. Sturdy enough to withstand 13.6 kilograms of resistance. Reasoning. A research study conducting strength testing on raccoons indicate that adult raccoons lift 13.6 kilograms of resistance. Results. Using a hanging digital luggage scale, we measure the door to resist at least 9 kilograms of force. 8. Operate under 70 dB. Reasoning. These numbers come from the sound intensity of a vacuum cleaner. Cats are often afraid of fireworks, thunderstorms, and vacuum cleaners, with vacuum being the most quiet of the three. Results. Using a decibel reading app, we measured the loudest part of the door's operation to be the clicking of the solenoid. Its peak at 40 dB from 1 meter away. Full system testing due to limitation on time. Full system testing was not conducted. Three. Architecture overview. Figure 1 illustrates a state diagram of the system. Blue states are for entering, green states are for exiting. For a cat wanting to exit, the PER sensor mounted on the indoor side of the cat door detects when the cat has moved close to the door. If it is not curfew, then the door opens. After the cat has passed out of range of the outdoor sensor, the door closes. For a cat wanting to enter, the camera detects and tracks movement, and PER sensor on the outdoor side of the cat door detect when a cat has moved close to the door. If it is nighttime, the light turns on. This helps the camera to produce better images to feed into the machine learning algorithm. The machine learning algorithm determines whether or not the door should be open. In the case that the algorithm decides the door opens, the door does not close until both sides see no motion on the PR sensor. Figure 2 depicts how the devices and non-electrical parts are linked. Blue indicates device and yellow indicates non-electrical component. Blue lines indicate wires. The diagram is drawn to a scale. Figure 3 describes how software and hardware components interact. Blue is hardware and green is software. Motion detection and tracking is implemented in Python and OpenCV. The machine learning algorithm is implemented using Python and TensorFlow. The inbound and outbound routines handle the PER sensors, power relay, solenoid bolt, and servo. The mobile app communicates with the Jetson through the MQTT protocol and is implemented using Xcode and Swift. Four, design trade studies. Motion detection. Motion detection is an important part of our project because we need to know when an object has passed in front of the door before we can begin to classify the object. While PER sensor alone can detect motion within a certain proximity, our primary method of detecting motion uses a motion detection algorithm on our video feed. The PER sensor acts as a secondary sensor which turns on the LED lights at night when something walks in front of it, providing the camera with sufficient light to send a visible video feed to the Jetson board. We choose to use video motion detection over a traditional proximity sensor because video motion detection provides better images to our machine learning classifier. In addition to detecting motion, when taking pictures of small animals from 1 to 2 meters away, the animal may take up less than 1 divided by 9 of entire image space using a traditional phone camera. By being able to detect where objects are in the image, we can crop that part of the image out and only send the cropped image to our machine learning classifier, resulting in a more accurate and consistent output. B. Machine learning classification. Our project ultimately aims to do facial recognition by examining the specific features of cats: eyes, ears, nose, fur, etc. However, due to a lack of available data sets, the time frame for the project, and the skill set that we possess, we decided that it was unfeasible to label features of the cats and train of those features in the time frame of the project. Instead, for the first interaction of the cat door, we are intensifying cats and allows them to enter and exit. Convolutional neural networks are the most popular and successful image classifiers today and acts as our machine learning classifier. Most convolutional neural networks use at least one of each of the following layers: convolution, activation, max pooling, fully connected, dense, and softmax interference. We decided that having one of each layer will suffice because the sample space of possible images is small. Our camera is stationary and is focused on an area close to the ground. Therefore, the classification naturally is more accurate and does not require a complicated neural network. Animal recognition research done at the University of Salina 12 showed that a convolutional neural network with one more convolution and activation layer that our neural networks successfully recognize animals on average 95% of the time. So our original goal was set 95% accuracy. C. Testing trade-offs. In order of preference, the testing options are as follows: live animals, taxidermy, video seeds, printing high-resolution pictures, and stuffed animals. Iren's friend has a cat and Jing's friend has a cat, but animals aren't allowed on campus. The best feasible testing method would have been to record footage of said cats interacting with the systems and the system responding approximately. For raccoons and the system responding. For raccoons, we were not able to find live raccoons to test our system on. The taxidermy raccoons is as close as we will get to a live raccoon, but they are expensive. We looked for videos of raccoons facing head first and cameras such as it's very similar to the video feed the camera will have captured of a raccoon. Stuffed animals are not desirable and as a test subjects because they do not look like real animals. A machine learning classifier that classifies a cat plushies, a real plushie, is a poorly built classifier. We are better off printing high-resolution photos of cats and raccoons. Unfortunately, high-resolution photos provide a set of images of cats that were sitting on couches or in grass. They were not entirely representative of what a cat would have looked like walking up to a cat door. D. Hardware trade-offs. We wanted to minimize the latency of our computer vision and ML algorithms because we want to be able to open the doors for a valid cat as it is walking up to the door without having the cat needing to wait. We estimated that the cat will be within range of the camera for a total of 1.2 seconds. Through our research, we determined that a Raspberry Pi will allow us to compute around 1 frame per second, which is too slow because we could potentially only receive one image during the 1.2 second span, and this image might not give a good indication of whether the animal is valid or not. Similarly, we looked into